Doc May.
Right. So good morning, everyone. Welcome to today's edition of the PAASE webinar. And so before we start, let's hear from Dr. Angeline Lau for the opening remarks.
Good morning, everyone. So, walang pasok ngayon, nagbumagyo. So on behalf of PAASE, good morning and good evening to some from US, or good morning to those who are in the Philippines. So on behalf of PAASE, I'd like to welcome everyone for today's webinar. First, I'd also thank Dr. May Lim, the chair of the Research Expertise Cluster on Mathematical, Statistical, Physical, and Data Sciences for organizing this lecture and inviting Dr. Mario Juvenal Onglao III as our research speaker. So I will quote, I'll use Press March used to align the lecture series that we will having this year to the vision that we have for the Pagtanaw 2050, which recognize the investigating the frontier research and emerging technologies that are essential in building our global competitiveness and innovation, being innovation driven. And by exploring the key technologies and scientific roadmap toward subhertz gravitational wave detection, this webinar highlights the cutting-edge advances in space science and quantum sensing while helping cultivate the expertise, research capacity, and innovation of the Philippines to contribute in this exciting frontier of science. So again, thank you for joining us. We hope you enjoy the lecture and have an engaging discussion afterwards.
All right. So today's speaker, and very glad he accepted this invitation, is Mario Juvenal Onglao III, who is an assistant professor at the National Institute of Physics, UP Diliman, and a visiting professor at the Center for High Energy and High Field Physics, SHIP, at the National Central University in Taoyuan, Taipei. He received his BS degree in Applied Physics, MS and PhD degrees in Physics from NIP UP Diliman. Through his affiliation with NCU, he recently joined the LIGO Scientific Collaboration and is contributing to CHRONOS, the Taiwan Gravitational Wave Detector Experiment. Now, Mario's research spans coherent metrology, interferometry, phase retrieval, and statistical fringe analysis, with a current focus on optical and electronic instrumentation for gravitational wave detectors and precision sensing. And so without further ado, the screen is yours, Mario.
Hello. So good morning, everyone. And I'd like to thank the organizers for inviting me to this webinar. So this is in fact my first interaction with PAASE, but looking forward to more in the future. Yeah, so thank you again for the opportunity. Let me just share my slides. Okay. Right. So on behalf of the CHRONOS collaboration, here today I'll just like to discuss the key technologies and science roadmap of CHRONOS towards subhertz gravitational wave detection. Uh, so I'm affiliated with both National Institute of Physics in the Philippines and the Center for High Energy and High Field Physics in Taiwan. Right. So just to add to the introduction of Dr. Lim, so about me, just until last year, I was a graduate student and instructor at the National Institute of Physics in the Philippines, where I worked in interferometric wavefront reconstruction and optics under the Photonics Research Laboratory, which you can see here in the upper right section. And then since August last year, I became an assistant professor in NIP and a visiting professor in NCU, where I will focus on the optics part of the CHRONOS detector in NCU. So in NCU, you can see the lab here at the bottom right side with the other CHRONOS collaboration members. Right, so as an introduction, when we think of space, how do we exactly observe the universe? So the simplest way is just to look up. So when it's at night, you look at the stars and you ponder about the universe. So the first method to observe the universe is using our eyes. If we want to become a bit more precise, we will use telescopes to observe the light produced or emitted by those celestial bodies. So the light you observe comes in many frequencies of the electromagnetic radiation, so this invisible light, radio waves, microwaves, etc. But for some objects, for example, black holes, they do not emit EM radiation. So for those objects, how do we observe them? So this is where gravitational waves come in. So when you have a massive object, it deforms the space-time. It introduces a curvature. And if you wiggle that mass, it will produce gravitational waves. Gravitational waves are tiny ripples in space-time created by the acceleration of massive objects. And the simplest way to do that, or one of the simplest ways, is to have two massive objects that are orbiting around each other, such as in colliding black holes and neutron stars. So this is not a new idea. Actually, 110 years ago, this was predicted by Einstein in 1916. So even if the idea is not that new, sorry, so this video of the uh, image visual representation of a gravitational wave. So even if the idea is not that new, the detection of gravitational waves are relatively recent. So the first detection of gravitational waves directly was performed in September 14, 2015 by the Livingston and Hanford Observatory in the United States. So here they observed a signal in both detectors, which corresponds to the theoretical prediction of the gravitational wave. So it took 100 years from 1916 to 2015 to get the first direct measurement of a gravitational wave. So why did it take that long? So that's because even if the producing masses are very massive black holes, when the signal reaches the Earth, it becomes extremely weak due to the large distance propagated. So when it reaches our planet, it produces a strain of 10 to the minus 21. So just to give you a scale of how small this number is, imagine the Philippines and you placed two masses at the uppermost and lowermost part. So that has a distance of around 1,850 kilometers. So for a strain of 10 to the minus 21, over that distance, you have to detect a change on the scale of a proton, which is 10 to the minus 15 meters. So that's very small. So the entire scale of the Philippines, you have to detect a change of a proton. That's how precise it has to be to measure a gravitational wave. So a gravitational wave changes the distance across the entire Philippines by only about the size of a single proton. Therefore, to measure this small wobbling of the space-time, we need sophisticated techniques. So how are gravitational waves detected? So in this case, I'll discuss the scheme used by LIGO uh, in measuring the first gravitational wave. So they need to use a special ruler, which in this case is the speed of light, since even if space-time changes, the speed of light will remain constant. Okay, so LIGO does that in this way. So a laser split into perpendicular 4 kilometer long arms here in the Y and X axis. And then the mirrors must be suspended such that they can be treated as free falling test masses. So when a gravitational wave passes through the detector, one arm will be stretched while the other arm will be compressed, therefore changing the distance traveled by the two arms. And then when we interfere or recombine the two laser beams, the difference in their travel times changes the interference pattern produced at the detector here at the bottom. So if the arms distances are equal, we will have constructive interference here. But if that changes, we know that one distance was changed. Right. But it's not that. So the description is a bit simple, but in practice, it's a bit more difficult because there are many sources of noise, and we have to extract the effect of the gravitational wave amidst that sea of noise. So over the years, the sensitivity of the LIGO detector has been increasing. So here is a depiction of the distance that can be covered by LIGO as it um, improves. So currently, it's around 170 megaparsec that can be detected by LIGO. So that shows that LIGO has shown tremendous success over the years. And but since LIGO is now approaching its design sensitivity, if we want to go even further or measure even more signals, we have to construct a new detector. So the feature detectors that are currently planned are here. I just show three. We have the ET, the Einstein Telescope, and the CE or Cosmic Explorer. So these are ground-based detectors. The key difference is they have longer arms. So LIGO has 4 kilometers. CE will have 40-kilometer length. Einstein Telescope will be a different configuration with 10 kilometers, but still very large. And then we have LISA, which is will be a detector in space with very long arm length. So for those detectors, here I plotted the sensitivity versus frequency. So as you can see, different detectors will be sensitive to different frequencies. So for the very low frequencies, the millihertz, we have the LISA. And for the high frequencies from 10 to thousands of hertz, we have the LIGO and ET and CE. But if you look here at the middle part between them, we have a bit of a gap where we don't have a detector that tackles or has a high sensitivity in that region. So that's where CHRONOS wants to contribute. It wants to focus on this gap between the millihertz and the high frequencies. So from zero point 0.1 up to 10 hertz. In this frequency band, we expect some new science, for example, intermediate mass black holes, stochastic gravitational wave backgrounds, and gravity gradient signals from seismic events. These three I will be discussing in more detail later in the presentation. Yeah, but that's the overview of where CHRONOS wants to insert itself. So just a outline of the presentation. First, I want to discuss what is CHRONOS, what are the key technologies unique to CHRONOS, and given that, what science can we expect, or what are our goal? So the information in this presentation can be found in the white paper, which was published just March of this year. So the project is relatively new, which you can access via this QR code on the slide. Right, so what is CHRONOS? So it's actually an acronym. It stands for Cryogenic Subhertz Cross Torsion Bar Detector with Quantum Non-Demolition Speed Meter. but let's just call it CHRONOS to keep it short. So this is a depiction of the CHRONOS setup. So we have a suspension systems here, which will be used to suspend our mirrors, and we have vacuum chambers here, which will be discussed a bit later. Right. So CHRONOS, again, cryogenic subhertz cross torsion bar detector with quantum non-demolition speed meter. It has three key technologies. So number one, it's cryogenic. So it should be operated at 10 Kelvin, hence requiring the vacuum chambers to keep it at that low temperature. So by using cryogenic operation, we reduce the thermal noise, which is dominant in the frequencies you want to tackle. Next, the cross torsion bar. By using a cross torsion bar instead of a free swinging mirror, we effectively lower the resonance frequency, uh, allowing us to access the lower frequencies. This also reduces seismic noise. And lastly, the quantum non-demolition speed meter. This allows us to reduce radiation pressure noise, which is again dominant in the low frequencies. So all of these technologies combined allow us to produce a setup which is just 10 meter by 10 meter, as compared to LIGO, which uses 4 kilometers arms. So the uh, geographic footprint of the CHRONOS detector is much smaller, which may lead to more possible sites for producing or for constructing gravitational wave detectors. And also, these key technologies allow us to access the subhertz frequency, where again, there's a sensitivity gap in that region. So I'll discuss these key technologies one at a time. So first, the torsion bar. So a torsion bar is just a two bars arranged in a cross configuration. Okay, suspended by a wire here at the center. So a gravitational wave stretches and compresses masses in this pattern here at the upper right side. If you just focus on the corner masses, we see that it follows this pattern. And then if you imagine that each mass is located at the ends of our bar, we can see that when a gravitational wave passes through our torsion bar, it changes the relative angle between our cross torsion bars. So if we can measure the angle between the bars, we can in effect determine the uh, gravitational wave signal. And another advantage of using a torsion bar instead of a pendulum is that it has a much lower resonant frequency. So for a pendulum, it has, or a typical length, so 10 meters, it has a frequency of 0.15 hertz. But for a torsion bar, it's much lower at 0.004 hertz. So by lowering the resonant frequency, we essentially can access the lower frequencies, because uh, anything below this frequency will be dominant with noise. So if we lower it, we effectively uh, uh, can observe a signal at the lower frequencies. Okay, so this is not a new idea actually. The torsion pendulum is already being developed in two other institutes, so TOBA in Japan and Torpedo in Australia. But they have slightly different technologies. So just to summarize the differences between Torpedo, TOBA, and CHRONOS, here I describe their thermal noise, bar thermal noise, quantum noise, and target sensitivity at 1 hertz. So for Torpedo, it uses room temperature operation, and it uses stainless steel with a 1 meter bar. So all those three gives us a 10 to the minus 16 sensitivity to 1 hertz. For TOBA, it's cryogenic using silicon with a 10-meter bar and a sensitivity of 10 to the minus 19. For CHRONOS, it is uses cryogenic and sapphire bar, allowing us to make the bar smaller at 1 meter. And it uses a speed meter in conjunction with the torsion bar. Those combined give us the sensitivity of 10 to the minus 18 uh, at, at 1 hertz. Right, so that's the torsion bar technology. So for the cryogenic technology, this is important because at the frequencies where we want to detect gravitational waves, this is dominated by the coating noise and the bar thermal noise. So the coating noise is the mirrors we use. If you have some temperature, the surface actually undergoes Brownian motion. So there is some uncertainty in the location of the surface. So if we want to reduce that, we have to lower the temperature of the entire setup. Similarly, the bar also uh, oscillates due to the temperature. So to reduce that, we also have to uh, lower the temperature. And lastly, for the quantum non-demolition technology. So right now, the current detectors are approaching the standard quantum limit since they have reduced the other noise sources to the lower. So if you want to quote unquote beat the standard quantum limit, we have to change the detection scheme where quantum non-demolition enters. Right. So how do we beat the Heisenberg uncertainty principle? So this one occurs when the two parameters cannot commute. So we have to choose to measure a parameter which commutes with the Hamiltonian. So in the previous or in LIGO, they measure the distance, which does not commute with the Hamiltonian, but instead we measure the velocity instead of the position. That will commute, so we can effectively beat the conventional standard quantum limit. So this can be observed here. So the Michelson measures the position, while the Sagnac interferometer measures the velocity. And this is again the uh, sensitivity versus frequency. So as you can see, if you use the speed meter, we have a higher sensitivities in the lower frequency. Okay, this is because we avoid the Heisenberg radiation, or sorry, back action, or the radiation pressure noise, which is dominant in the low frequencies. So how do we measure the speed? Essentially, we hit our mirror twice at different times. So since we measured the phase at different times, uh, we effectively get the time derivative of uh, our position, which is the velocity. So this is for the speed meter of a hanging mirror. If we were to implement this for a torsion bar, it will look something like this. So we have two lasers propagating in clockwise and counterclockwise directions, where each of them hit the bar at two different times. So since we sample it at two different times, we can effectively get the time derivative. By doing so, we can implement the quantum non-demolition detection scheme. So combining all those three key technologies, this is the predicted sensitivity of CHRONOS, accounting for all the different noise sources. So 1 hertz or 2 hertz, we achieve a 10 to the minus 18 sensitivity, which is sufficient for GW detection. Right. So with that sensitivity and for CHRONOS, what can we expect from the science? So what questions can we answer? So the main goal of CHRONOS is the gravitational wave detection, but along the way to that sensitivity, uh, it's not a barren desert. We have some science which we can do at each phase of the CHRONOS project. So the initial phase for the construction of the instrumental setup, we can perform quantum science experiments, which I'll discuss in a bit later. After that is the gravitational gradient. So this one requires a bit lower sensitivity compared to gravitational wave. So on the way to that sensitivity, we can detect Newtonian noise and the gravitational fluctuations produced by earthquakes. And then lastly, for the gravitational wave at the target sensitivity of CHRONOS, we expect intermediate mass black hole mergers as well as stochastic gravitational wave background. So for the quantum science, CHRONOS is a unique setup where it's a macroscopic system with large mass, where we can expect to observe quantum effects. So it can be a platform to probe the macroscopic observation of the quantum effects, which allows us to bridge the transition from quantum to classical regimes. Next, for Newtonian noise. What is Newtonian noise? Newtonian noise is the fluctuations in the gravitational field of Earth due to human activity, atmospheric fluctuations, and seismic waves, among other causes. So, for example, when the atmosphere changes density, it will change the gravitational field of the Earth, which can be detected by CHRONOS. Similarly, when the ground density changes due to seismic waves, it also changes the gravitational field, which can be detected by CHRONOS. So if we can estimate these two and then observe it in CHRONOS, essentially we can perform experiments on measuring the Newtonian noise, or at least estimating the Newtonian noise, which will allow us to model the Newtonian noise, which will be very useful for future gravitational wave detectors if they want to mitigate this noise term here. And another scientific opportunity is in the early detection of earthquake. So when an earthquake occurs, we have a rapid mass distribution, which changes the gravitational field, which can then be detected by CHRONOS. So just to differentiate this one, it's different from seismometers, since seismometers measure the displacement of the ground itself. But for this one, it measures the change in the gravitational field. One advantage of that is that gravitational wave travels at the speed of light. So if we can detect this one early, uh, we can detect it before the seismic waves arrive, giving us a chance for early detection of earthquake signals. So here in the plot is some earthquake signals at different magnitudes, overplotted with the sensitivity of CHRONOS. So as you can see, for magnitude 6 and above, the signal lies above the CHRONOS sensitivity, meaning we can detect those magnitudes. And here at the bottom is if we place CHRONOS here at the institute in Taiwan, we see the distance where we can detect certain magnitudes of earthquakes. And for a magnitude of 6, we essentially cover the entire Taiwan region. And since this is more relevant to us, what if we place CHRONOS in UP Diliman? Here I plotted the SNR equals 3 curves for various magnitudes. So for 5 until 7. So for a magnitude 7 earthquake, we have this detection area here. And I've also plotted here the historic earthquakes from the past 10 years, just to give us an idea of how many earthquakes we can detect if we were to place CHRONOS at UP Diliman. And also the recent earthquake in Jansan, with the 7.2 magnitude. If we were to detect it with CHRONOS, for SNR 1, 3, and 5, this is where we have to place the detector for those SNR. Okay, and then for intermediate mass black hole mergers. So why is this important? So currently, intermediate mass black holes have a large uncertainty in the data, where the population and origins are not greatly understood because we it is hard to observe them. So one way to aid or to contribute in the observation of intermediate mass black holes is through CHRONOS. So intermediate mass black holes in the late in spiral phase, that frequency is inside the sensitivity band of CHRONOS, which means we can detect that late in spiral waveform. So that's crucial because if you remember the other detectors, the LISA and LIGO, they have different frequency bands. So for the lower frequencies, LISA will handle that. And then when the waveform reaches the middle frequency, CHRONOS will then focus on that sensitivity. And then in the later stages of the merger, LIGO will then handle that region. So by having detectors in multiple frequency bands, we can effectively track the evolution of the gravitational waveform. So here we plotted the distance versus mass for different SNR. This is basically the maximum distance where we can detect mergers with total mass, m total. And here on the right is the signal of different mass mergers overplotted with the chronosensitivity in the blue curve. So we can see here that for some large masses, for example, 10,000 solar masses mergers, some part is above the sensitivity, giving us the potential for detecting those. And at higher masses, we shift to lower frequencies and but a higher SNR. And lastly, for the stochastic background, so stochastic background is these are the unresolved sources where we are not sure uh, if they came from a black hole merger or some other sources. So this could be from um, signals from the early universe. So to estimate the stochastic background, we need to perform measurements at the different frequencies. So uh, to cover the entire landscape, we need detectors at multiple frequencies, which again, CHRONOS can handle in the subhertz frequency. Also plotted here is the different detectors. So LISA is the blue one, LIGO is the red here. And at the lower frequencies here, we have the cosmic microwave background detectors. Right. So just to give an overview of where CHRONOS is currently, this is the plan for CHRONOS or the different phases. So phase 1 is just about complete. So this was done by the members before I became part of the collaboration. So the R&D for key technologies was for the past 5 years. And until 2033, we will perform integration tests where we will construct the detector and just make sure that everything is working. And then, or make sure that the technologies are working as intended. And then phase 3 is the construction of CHRONOS in the underground lab. And in 2035, we uh, hope to have a observation during that year. But even in these phases, we were able to publish or submit some papers. or where some of them have been accepted and some have been uploaded to archive. So as you can see, there's many things that can be done in CHRONOS. So if ever you're interested in collaboration, we are very much open to discussing things with you. And here I also show the observatory in Taiwan. So this is the current state of the interferometer, where we build it one technology at a time. So instead of building the cross torsion bars adjunctive interferometer right away, right now we have a Michelson test where we test the input optics which will be used. So once this is tested, we can then upgrade the interferometer to the torsion bar. Then here in the lower left is the remote control room where we can control the parts of the interferometer, as well as showing the other members of the CHRONOS collaboration. Right. And I'd also like to invite the members here to a International Gravitational Wave Summer School this 2026. So it will be held on August 17 to August 31. And the registration will be until July 31. So just a fact here, I attended this one last year and it was very informative. It's a hands-on experiment where uh, we use the same systems that LIGO uses, but for CHRONOS. And it gives a very good overview on the technologies used and uh, the terminologies. And you can actually touch the interferometer that we will use. So if you're interested in attending this Gravitational Wave Summer School, you can register using this QR code here or email the PI, Professor Yuki Inoue, using this email address here. Right. So just to conclude this seminar, so I reviewed the importance of gravitational waves and the challenges of detecting their extremely small space-time distortion. I introduced CHRONOS, the next generation gravitational wave detector, a concept that combines cryogenic operation, torsion bar sensors, and speed meter interferometry to achieve high sensitivity sub-Hertz frequencies. And I highlighted the scientific opportunities enabled by CHRONOS, including advances in quantum measurement, studies of Newtonian noise, detection of earthquake gravity signals, observation of intermediate mass black holes, and searches for the stochastic gravitational wave background. So that's the end of my talk. Thank you all for your attention. So the floor is now open for questions.
Thanks a lot, Mario. That's a very nice talk. So the floor is now, as Mario said, the floor is now open for questions. Just raise your hand and I will call you. Yes, Sec Boy.
Okay, so as May had earlier indicated during the introduction, PAASE has been involved in the external review of the Science, Technology, and Innovation Foresight document, which is up to 2050. And I expect that PAASE will still be involved in the updating process. Did you get that, May?
Yeah. Yes, we can hear you. We can hear you.
Yeah. So I was just wondering anong mga areas doon, yung mga key operational areas in the science, technology, innovation, foresight ang pwedeng magamit itong mga studies na to. Of course, I suppose this will be useful in parang disaster risk reduction management. It may be useful in the inventory of resources that may be found under the sea, and it may also be a good topic for our I don't know, our astronomers or meteorologists. I'm not sure, but for example, we have helped establish an astronomy center at Rizal Technological University. I don't know whether they will benefit by attending into this August 17 seminar. So, yun lang, I'm interested in finding out saan magiging useful itong mga studies na ito in relation to our key operational areas in our science, technology, and innovation foresight document, and also to find out who may benefit from attending this seminar that is scheduled on August 17. Thank you.
All right. Mario, do you want to take that, or should I try? You should go first, and then I'll
Yes, yes.
say
Thank you,
something
ma'am.
after.
I'll try it first. Thank you very much for the questions, Secretary. So for the first question of, I'm not exactly sure of the key areas, but
Mm.
as you mentioned in the disaster risk reduction management, it could have some application there, particularly in the early earthquake detection. Uh, and also for the Newtonian noise modeling, that can be used for tracking the ocean motion, some ocean waves and
Mm.
the atmosphere. But for the specific applications, I think more modeling can be done. So if we can model what effects we can expect, we can then check if it's within the sensitivity of CHRONOS. Just to
Sa,
see if
yeah.
it can be detected.
Sa climate change, may epekto ba yan?
Siguro po yung 'pag nagbabago po yung temperature ng atmosphere, kung ano po yung
Mhm.
magiging, change niya sa atmospheric fluctuations, kung
Mm.
made-detect ba siya dun sa, chronosensitivity. Baka possible, interesting question po yun.
Okay, thank you. The second question is yung who will benefit from the seminar that will take place on August 17?
So, yung sa August 17 po, from experience last year, it focuses on hands-on. So, what actually happens during the seminar is it gives an overview of um, gravitational wave detection, kung ano yung technologies yung ginagamit. And then it
Dito
uh,
sa mga agencies dito sa atin, which agencies might benefit from this?
baka ano po,
PBORCS ba? Or
I think iba, baka hindi po ako exactly sure, pero baka iba po yung systems na ginagamit ng
Mhm.
PVOX.
PBORCS, oo. Sa pag-asa,
Baka
wala.
sa baka sa pag-asa meron po
Meron
kung
din.
opo.
Okay. Oh,
Yeah.
sige. I'm very proud of you, Mario. Okay, you should see my son, your cousin, who is an associate professor of industrial design diyan sa College of Fine Arts. Kailangan magkita kayo. Okay, thank you.
Sige po. Thank you pa.
Sige. Thanks, Ekboy. Are there any other questions from the audience? We can entertain them. Okay, so while waiting for okay, Al, go ahead.
Thank you, Angie. Good talk, Mario. Again, I'm the same interest as Tech Boy has, looking at upcoming technologies. I was listening to another physicist yesterday at the National Academy, John Vic. Also very low cryogenic temperatures. Uh, and prior to that, we were dealing with quantum ventures already in quantum technology and devices and detection. First question on the gravitational waves. And definitely, I read something about the earthquake in Fukushima that they detected the shift of the island of Japan. Which instrument did that measurement, considering that yours is not online yet for another 5 years or 7 years? Sino nag-measure no? Do you remember? Do you know? Have you read that? First, and of course, yeah, I assume that's your space. Are you familiar with that disclosure, or it was in the news? I think that they showed that during the earthquake it shifted the whole island. uh,
Yeah.
I'm just
So
wondering what measurement did they use and which of the instruments that were outlined in your talk were even part of that measurement.
so I think I'm a bit, maybe I've heard or read some of the paper, but I'm not sure of the exact details. But some candidates, I believe, for the detector could be number one, maybe Kagra, the gravitational wave detector in Japan, due to the proximity. And I've also read some superconducting gravity gradient meters. So that one can also be used aside from the torsion bar. So it's a different setup where we have a superconducting uh, a capacitor essentially that can measure the uh, the ground motion. Yeah.
Okay, so was most likely indeed the Japanese, but and there are no existing Taiwan. We were in Taiwan last year. I'm not aware of an ongoing activity. It's only now that I actually made aware that there's a gravitational effort measuring in Taiwan. Well, but there are no existing equipment in Taiwan right now that is capable of doing such measurement.
Yeah. From our knowledge, this is the first one in Taiwan for the gravitational wave detector.
Okay. And since we're talking about 2050, as Secboy indicated, no, I mean, I'll put a moonshot here. Would this have some capability of predicting, uh, indeed, uh, shift or most likely to happen event? Okay, clearly, from the disaster point of view, I was with Mahar Lagmay yesterday and we're already pointing out resiliency and control capability for prediction within a day based on the information that's coming in from Project NOAA in order to alert the farmers from an impending disaster, but more to pacify them, not to kill themselves with it. Pag nabaha o nasira yung crop nila, they'll be in despair. Most of them, like in India, they used to kill themselves. Nagsisisyan yung mga, ano kasi nasira yung ano nila, yung mga pananim nila. But in this case, by having a predictive capability, we can alert the farmers that, especially if they're covered by insurance, to not be in despair. That will compensate them immediately for such an effort. So, ganyan yung application. That, of course, that's on the ground now. We're trying to look for implications. Same way they're using space technology now, being able to predict and also validate existing disasters in Thailand. I was there last year. They're using satellite pictures to validate faster for GIDA areas to say, okay, nagtanim based on the satellite data, then it was destroyed based on, okay, pwede instrument. Ganon tipo. Now, this is more of a grander scale. This is far more sensitive, even for, say, terraforming and doing the recto bank in our eastern side. Wala tayong kalaban dyan. The eastern Philippines, you know, at Benham Rights. No? What would it take to actually elevate that? Is another big area for potential increased exploration as well as utilization. No? But is there something that you know that can, one, enable that, or how does your current science going to be useful for such activities, if any? So medyo futuristic yung question, but definitely a challenging scientist as well as engineers, young one, who not naman justify, but project where your science is going to be good at or potentially helpful. So that's the question.
So if I'm correct, this is about the predictive power of the detector. If it
Yep.
can be used to aid in warning the farmers before the earthquake
I know
or
that's not the farming part. Because the farming, you can do that with Project NOAA right now. But if I were to
yes.
say, okay, I use CHRONOS, for lack of a better word, I use CHRONOS, I scan the whole recto back, which is the size of Luzon. And there has been no disturbance or gravitational wave in that area. That's very stable. Hence, there's no earthquake there. Hence, we can develop that area and put up thousands of windmills, for lack of better, power wind turbines. Ganon klaseng predicting capability. Kaya mo ba yun? Or kaya ba ng Chronos to be assuring on top of existing technologies and tectonic plates and all of that other science? that's already in existence. I'm just trying to project what your technology, what you're learning right now, what is it good for?
Yeah. So for earthquake, there's some overlap with the current seismometers and CHRONOS. Just one difference of CHRONOS is it can detect earthquakes faster, since
Okay.
the signal propagates at the speed of light compared
Yes.
to seismic waves.
And
But if
sensitivity-wise, Mario, pareho? Or mas magaling yun sa inyo? Sensitivity.
uh, I think sa ngayon po baka similar po siya. Kasi
Pareho pala.
uh,
Okay.
yung
Sige. Ano na pa?
ano rin, I think the Chronos will also be more expensive compared to seismometers. So if we talk about coverage, it might be easier to just put many seismometers as compared to the same number of Chronos to cover the same area.
Okay.
So for
Okay.
predictive or tracking the earthquake activity, uh yeah, but there's some overlap between the two technologies. So, but I guess one advantage of Chronos po is it's not specific to earthquake or
Yeah.
ground
I know.
motion,
Yep.
since it can also other sources of gravity fluctuation. So the changes in the atmosphere or um, changes in the groundwater or some distance. But for prediction, it depends if detectable po yung small changes before the big slip, yung
Okay.
malaking fault.
So I'll move out of the Earth, Mario, in terms of say, you watch the movie, Don't Look Up, no?
Ava,
Where you have comets and
ava.
people. Is there use for that? If there's an incoming, uh, what do you call that? Extinction level comet coming in. This cloud is going to be helpful in detecting gravitational waves of an impending that we can't see. May gamit na yun doon?
There may be some possibility if we have many chronos. Because if you only have one, it cannot localize the location. So we
Okay.
need multiple
Kailangan
to uh para po malaman kung saan nanggagaling.
para magta-triangulate ka.
Okay.
I saw Reyna
Opo.
Reyes also yesterday. And now with the space agency. Maybe we ought to connect all of your findings with her
Opo.
black hole discoveries early on and how we can combine it with your technology. Okay, I'll stop there. Thank you for giving us a talk. I mean, I always like listen to young scientists in PAASE, no? I've been part of PAASE for quite a while, and definitely it's nice for me to see the young guns coming out, led by, of course, Angie and May. Salamat, May at Angie. Nandito kayo. Keep it up. Thank you.
All right. Thanks, Al. Angie, you have a question.
Yes, so Secboy and Doc Al mentioned the Pagtanaw 2050. So actually the lecture series this year, the aim is also to add no as our commitment no for Pagtanaw 2050. So yes, Secboy, we will do our job or our mission no to do lectures and toward this aspiration no, for Pagtanaw 2050. So aligned to that, my question to Mario will be, how do you envision the role of Filipino researchers, no, and or Philippines as a whole, so in this Chronos project, and especially for the next 25 years. So you presented this projection no, for the next few years no, of this Chronos project. Since Secboy is here, maybe you can already tell what capabilities or investment should we begin building today so that we, the Filipino researcher and Philippines, become a major player, or we will also be a major contributor for this scientific endeavor.
Thank you for the question po. So, in current discussion in the Chronos collaboration, yung na-assign po sa akin is yung optics part. So, mag-develop ng um, output mode cleaner dun sa setup na gagamitin sa Taiwan. As well as yung quantum measurement, parang i-test po siya dito sa Philippines. And then pag okay na siya dito, tsaka siya co-construct din sa Taiwan. Aside from that, pwede rin po exchange ng mga students in the future. So magte-training sila doon or pupunta rin dito for training. But yung end goal siguro is magka-CHRONOS din sa Pilipinas. So gagawin sa Taiwan pag okay na po siya, i-replicate po natin dito. So meron din po tayong gravitational wave detection, which is I guess, an ambition for the future.
For that ambition, what will be your wish? Parang ano yung sa wish list mo?
Well, ano po, funding. Kasi ang dami pong marami pong kailangan na gamit to
So-
build it. One step at a time.
Sige. Can you elaborate on that? Ano yung mga one step at a time, and usually how much does it cost? Let's ask it.
Yeah, this
So,
might be the right platform.
yung exact amount, since
Ballpark.
na-mention lang po ni Professor Yuki in the last SPP, he estimated, I think, 20 million NT dollars. Or
Magkano yun in pesos?
mga ano siguro, 40 million.
Over what period? So how much does it cost to build? And in building blocks, and how much does it cost to maintain?
Yeah. So the large capital, I think, is in the chambers, vacuum chambers. Kasi kailangan po ng malaki. Nakasya po yung lahat ng gamit. So, per mirror, may sarili siyang vacuum chamber. So, if ipakita ko po yung slide ko kanina. Punta lang po ako dun sa, actually, sorry, ang daming appendix. Ito po. So, kailangan po ng malaking vacuum chamber here.
Wait, we're
Which,
seeing the hands-on experiment, the summer school slide.
I see. Mag-reshare po ulit ako. Nagbago po ba?
Hindi pa rin.
Yeah, but from what I remember, yung isang chamber po mga 700,000 NT dollars, so mga 1.4 million.
Sasabihin ni Sec Boy, kayang-kaya yan. But what does it take in terms of manpower as well to have a network of so I guess the part ng question na yun is your prototype would cost that much, and if one were to have a network, sorry, hinajak ko, Angie, yung question mo. If you were to have a network of these, what is the network size that would be useful for big a collaboration, let's say, within the Philippines, as well as to do detection that might need multiple yung pag-localize, for example. What would be the typical size number of CHRONOS setups, for example, here in the Philippines, taking into account that, yes, it will take time to build it and all to test, to integrate. So, how much in cost and time and people do you think it would need?
So I guess once na gawa na po yung sa Taiwan and familiar na, it will take a longer time to construct same setups. Well, minimum is 3 for triangulation. But we also have to consider po yung distance between the detectors. Kasi if masyado pong malapit, hindi magiging effective in triangulation. So, i-check pa po if baka enough na po isa sa Pilipinas tapos yung next one is sa ibang bansa na para ma-efficient yung pag-triangulate pa.
Okay. Excellent.
And for the manpower, it might be a bit unrelated, but it will be very helpful if there's support in sending students or scientists to Taiwan if ever to study. Since right now there are very many things that can be studied since the project was just started this year. There are still many studies that can be performed. So if there are interested groups, I think um, if they have funding to go or to contribute to stay for a long time in Taiwan, that will also be very helpful.
Thanks, Mario. Sorry, quick question. Ano yung cryogenic temperature? What's the what's the temperature that this CHRONOS is operating in?
10 Kelvin.
Okay. Sorry. Okay. So Angie, do you have a follow-up to the earlier question?
No, thank you. That's perfectly good. So this record is actually streamed live at Facebook, and it will be also uploaded in YouTube. So we will actually be sharing it also to Science High School and DepEd, so that more students can also watch the video, and maybe it will also inspire them to pursue this field.
All right. Ooh. Thank you. Thanks. I have a few more questions, but I think we can do we have time, or should we now start wrapping up?
I think there's one questions chat box.
Oh, sorry, I missed
Maybe
it.
we can.
I did. Okay. Interesting. Ayan, interest from LJ. Sorry, I can read. LJJL Bondok. Interesting talk, Dr. Onglao. Just curious, is there a theoretical physics calculation that predicts that low Hertz gravitational waves can be used to predict some of the properties of dark matter and indirectly that of dark energy? Thanks for answering.
So unfortunately, I'm not that familiar with the theoretical calculations used, but I know the Professor Inoue is in discussion with some other scientists, particularly for dark matter. So I think there's some possibility there to if we can or if we can use the detector in dark matter, dark energy studies. Yeah, so I think there's some interest there, or some possibility.
All right. Thanks for that, Mario. So it's a really great talk. And let me just check the schedule. So if there are no more questions, we can now give Mario a certificate. I think if there are more questions after this, please feel free to email Mario. And now let's, okay. So we present this certificate. So PAASE presents the certificate of appreciation to Mario Juvenal Onglao III, PhD, for being our speaker in the Philippine American Academy of Science and Engineering webinar titled Key Technologies and Scientific Roadmap of CHRONOS Towards Sub-Hertz Gravitational Wave Detection, held on July 10, 2026, presented this day with our deepest gratitude from Dr. Maria Margaret Q. Peña, President 2026-27 of PAASE. Okay, thank you so much, Mario. And now I think we are going to go to our photo op. So if everyone can just turn on their cameras for a bit.
Okay po. 1, 2, 3. Smile. Another one po. 1, 2, 3. Smile. Okay na po.
All right, thanks, Feb. And so with that, today's webinar is concluded. Thank you very much to our participants, to PAASE, well, especially, of course, Mario, to our participants and everyone who asked questions. Thank you very much. We hope to see you again in the next webinar, and we'll send an announcement soon. Thank you.
Thank you, May. Thank you, Mario.
Okay, thank you
Bye.
po for the opportunity. Thank you po.